Hello students, welcome to class 30. Okay, so today we will go for palladium organopalladium reagent in organic synthesis. So the first organopalladium used already we have learned, that is our Wacker's process. Okay, so in this we have seen that how which was been discovered in 1957. So we have studied here how the alkanes were converted to aldehyde and ketones. Okay, so this was in the presence of CuCl2 and palladium chloride. Okay, and in the presence of oxygen and water molecule. So this is how we have seen. This is a co-catalyst we have used, and this is a co-catalyst we have used copper chloride and palladium chloride as the catalyst. Okay, this is what the important palladium catalyst we have used in this Wacker's process, where you can see that when we take any of the alkanes, okay, in the presence of the catalyst, this palladium, 10 mole percent 10 mole percent palladium chloride in the presence of copper chloride and solvent DMF, okay, presence of oxygen, water molecule. So you are going to get a ketone here. Okay, and the same thing we have seen that if there is no oxidant used, okay, so we are going to find the aldehyde like this. So this is your aldehyde and this is the ketone. So like this, from the Wacker's process we have seen that the aldehyde and ketone is being manufactured in the presence of the organopalladium catalyst, that is your palladium chloride here. Okay, so similarly in another case of manufacturing, you can see that you take this secondary alcohol, okay, one secondary alcohol olefin compound. Again, when you treat this with palladium acetate, okay, PDOAC, in the presence of oxygen and water, okay, palladium chloride, not acetone, we will take it PDCl2, and in the presence of CrO2, that is chromium oxide, I will write here PDCl2, CrO2 as oxidant, chromium oxide as oxidant, and water, and after refluxing finally treated with concentrated Cl. So we are going to get something in this way. Oxygen we are going to get here like this. Okay, so this is alpha beta unsaturated ketone, alpha beta unsaturated ketone we are going to get. So this is one of the use of our organopalladium catalyst, where we can see a secondary alcohol is converted to alpha beta unsaturated. Alpha beta unsaturated here also you can see this is going in, this is functional group is removed, and you are going to get the alpha beta unsaturated ketone in the presence of oxidant here, chromic oxide, and in the presence of organic palladium PDCl2, and finally treated with the concentrated HCl. Okay, so this is what the one more organopalladium used for conversion of secondary alcohol to alpha beta unsaturated ketone. So one more reaction we can show, that if you take this compound, so where you can see this alkene is there, so where this is the terminal alkene, this is terminal alkene, and this is your internal olefin. Okay, and when this is treated with the palladium OC twice, here yes palladium acetate and in the presence of oxygen, okay, and H2O in presence of ethanol and at 60 degrees centigrade temperature. So you can see that this product is going to happen where you get the ketone, and this is going to remain as it is. So 90% yield is obtained of this of the product here. So the terminal double bond is being converted to ketone, whereas the internal olefinic the structure is remained as it is. So this is one of the regioselective product, very selective regioselective product we are going to get here, and there is no isomerism shown in this case like this. Okay, so this is one of the another example where we can see how the organo palladium catalyst works in this type of conversion of only the regioselective terminal alkenes into ketonic part, and here you can see even the steric hindrance plays the important role here. Okay, steric hindrance is important part here, and that's why further conversion of this internal olefin is not possible. So a regioselective type product is obtained in this case, and even in another case of the example of another example. So if you take this this compound, and if you treat this alkene compound, so if you treat this with the Waker's Waker reagent, that is your palladium reagent, and if you go for some oxidation at room temperature, so you are going to get something ketone, and this remains as it is. See, so now this is nothing is happening here, but at room temperature Waker's reagent with palladium chloride, copper and oxygen, so this part is converted into ketone here. Okay, now if this product, if you heat for 50 degrees centigrade, now you are going to get something. This is your ketone, 3 1 2 1 2. This is your ketone, and here also part OMe. Here you can take it, don't take it. Okay, so this is what I'm going to get a diketone. Okay, a diketone is got here. So this is how at higher temperature you can see that this part is also converted to keto group here, and this part already there is a keto group here, and this remains as it is. Okay, so this is how we can say that at higher temperature you can see that both the alkene group is converted to double bond is converted to keto group here. Okay, but at room temperature only one part which is little bit sterically not hindered, this is going to convert into keto form. Yes, now in another case of example you can show is this example you can take this example. You take here like this methyl group, this, and if you treat this with palladium chloride, copper chloride in the presence of dimethyl formamide, water, oxygen. Okay, so this is a compound olefin compound, methyl group is there, and 1 2 3 4 5, so it is a 1,5-diene. Okay, so 1 2 3 4 5 1,5-diene, and you use this reagent, Waker's reagent, so you are going to see that, so you are going to end up with, see here like this. Okay, so here 90% of aldehyde is obtained here. This is a fascinating to observe here, very important. So 90% of aldehyde is obtained here, though this condition of oxygen and oxidant is used in this case. And this is because of maybe the very steric hindered group added here, and this is not happening any this is not going to happen, is going to change here, but this part you can see this was observed that the terminal alkene is going to be is converted to aldehyde or aldehyde compound here, and it was found to be 90% of the yield was being obtained in this case. Okay, and no doubt if for further drastic condition, if it used like in previous example what we have seen with temperature and refluxing with some no doubt we are going to get the diketones, but the major product in this case obtained after low oxidation here, so aldehyde is obtained here. So like this, so this is how this is what because of this nature I have taken this example to show that not only always the ketones will be formed whenever the oxidant is used, but sometimes some examples are such that the adverse is going to be the product in the major product here. So this is an example to understand. So next you can show off another example, that is your Trost reaction. Trost reaction, TROST. So where you can see this is your halide, and if you treat this with palladium catalyst, so you are going to get something acyl complex here, where palladium is going to be attached in the acyl group, and when this is treated with the nucleophile, you can see it is going to attach at the terminal A. So here nucleophile is attached at the terminal of the carbon here, and this is X is going to be taken by this palladium, where you can see a pi allyl complex is formed as intermediate. Pi allyl complex is found as a intermediate here, and the final you can see here. So this product is got where the X is a leaving group here. Okay, and nucleophile you can use of any of the functional group in the, acting as a nucleophile, and ultimately you are going to see that this nucleophile whatever you are generating, so it displaces the leaving group and is going to take place of the terminal carbon here, alkene here. So this is what and with following the transition pi allyl complex transition. Okay, so this is what the example of the Trost reaction, where again you can see that the organopalladium catalyst is worked in a very important way here to get this nucleophile attached to the terminal carbon alkenes. Okay, so this is a very important example. Followed by next we will go for Heck reaction, which is also called as Mizoroki Heck. Okay, so for which he got in 2010 Nobel Prize. Okay, so this is what Heck reaction, where you can see that any aryl halide is treated with in the presence of palladium and PR3, okay, trialkylphosphine. So in the presence of diethylamine, so you are going to get this compound, something like that, plus you are going to get R. Okay, so here, so we are going to get the 2-olefin product here when the in the Heck reaction, when this is treated with the aryl halide with the olefin compound. So in the presence of palladium trialkylphosphine, in the presence of a base, so you can see that this product is obtained. Also this one not here, so you can take another compound, not a ketone here. So double bond C double bond R function with any functional group here. So like this, the 2-olefin is formed in this case here. Similarly, one more you can take in the presence of palladium 0 PR3 Et2N. So you are going to see this one double bond, another double bond. Okay, so this is what a conjugated diene is got here, like this. Okay, so double single double, yes, so conjugated diene is obtained in this case here. So type of this is how you can see that the Heck reaction is taking place here. So where you can see from this compound, okay, so this type of olefin compound, you are going to see that with the release of this leaving group, so this is coupled here and you are going to get a conjugated diene here. So this is how we can see that the Heck reaction is playing is very much important here to get the product here. Now if you see, so one mechanism of this, okay, so one mechanism I will go if an examination it comes, so you can show this one mechanism. Okay, so to get the 4 to 5 marks is going to come in this. So this palladium catalyst, organocatalyst will first be treated with this oxidative addition with the aryl halide here, and oxidative addition takes place here, and you are going to get something L. So palladium is going to attach for this the catalyst going to attach for this aryl halide here, and you are going to get this compound first. Now if you add olefin here, another part, so what will happen now? Next you are going to see that you are going to get this olefin compound attached to here, okay, and this L attached here, and this remains as it is, and palladium will have the X whichever is obtained here, obtained in the previous step. Now here what happens here, you can see alpha beta migratory insertion, okay, so here alpha beta migratory insertion happens, and you are going to get something like this. This is your palladium X, and this is your R H, and you can see you are going to get something H and here H like this. Okay, so this is what you are going to get this compound upon this rotation. Okay, to get easy formation of direct elimination process, and this, so something you are going to get in this way. This is your palladium, this is your R H H H like this. Okay, so this compound is the same like here, but this is how after rotation you can see that it becomes very easy for elimination now. And now this part reductive elimination takes place, where we are going to get this required compound, or this one, and you can see this happens only by beta hydride elimination. Okay, so beta hydride elimination, so we are going to get the required compound here, and the other thing is left as it is with X here and hydrogen here. Okay, and finally you can see there is the removal of HX, and you are going to get palladium in the form of zero state. So this is how the product is got in a Heck mechanism. So this is one you can show in the examination. So see here we have started with palladium. Okay, so first it reacts with your aryl halide, oxidative addition takes place, and you can see here, so halide alkyl halide, and palladium is going to join here, and this X you can show is here, so you can show here is bonded to this. And second is you can see that the alkene is going to be inserted into this palladium, and you are going to get this compound where alkene is added here, and and you can see the other thing will be as usual. And next is you can see here, so this is transformed here to undergo alpha beta migratory insertion, and you can see here the double bond is is collapsed here because of this migratory insertion, and you are going to get this this type of arrangement, this arrangement on the rotational way. So because for the elimination it becomes or to understanding, so this is how we can understand the same thing this way. Now finally beta hydride elimination takes place, so one of the hydrogen is going to attach with this palladium, so wherever here this one, so with hydride elimination we are going to get this, PDX is there, one of the hydrogen is attached to it, and other thing, when this goes, it forms a double bond here, and other thing comes as a product here, as we have seen in the Heck reaction there, and finally this is got, and finally you can see that HX is been formed here with again the parent compound palladium 0 in the state, ready for the next cycle, like this. Okay, so this is how we can show one of this reaction in the examination, very Heck reaction. So this is how the organopalladium catalyst works in most of the synthesis of organic chemistry. So one more organopalladium is used in one of the example. You can take this Br. This is deuterated bromine benzene D. This is all D. Okay, so deuterated bromo benzene. So when this is treated with methyl cinnamate, so you can take in this way. So this is your methyl cinnamate. Okay, methyl cinnamate. So if you treat this plus, I will write here. So this is your methyl cinnamate, and this is your deuterated bromine, and the catalyst used here again, the palladium catalyst, if you use here in the presence of butyl phosphine in the presence of dioxane as a solvent here, and a base dimethylamine. So you are going to get this compound pH something CO2 Me with here double bond here, and all like this. Okay, so you are going to get this compound here. So this is how you can see the single isomer of this is got. Single isomer is obtained in the presence of methyl cinnamate reagent and deuterated bromobenzene, and you can see that this will leave. Okay, and this is going to react with this, and this happens only in the presence of palladium organopalladium catalyst in the butyl phosphine dioxane as a reagent, and base dimethylamine as a base. So this is how one more reaction, organic synthesis, we can see that the role of palladium reagent takes a very important role here. Similarly, in one more example, so many examples are there. So in the examination, you can provide any of one of the example or two examples looking at the marks. So you can see that you can provide any one of the examples. So in the presence of acetate here and triethylamine base palladium acetate, so you are going to get the coupling type of mechanism. So like this. Okay, so this is your benzene 6 membered, and this is what you are going to get, a racemic compound here. Okay, so racemic type of compound you are going to get here when this cyclohexene is treated with the iodobenzene here in the presence of palladium acetate, okay, and triethylamine. So you are going to get a racemic mixture of this, where the benzene ring is added into the cyclohexene here. So like this. Okay, so this is also happens in the presence of palladium acetate and in the base. Okay, so like this, other things as usual, Negishi reaction is there, Negishi coupling. Okay, Negishi coupling also you can show, where you take alkyl halide and you treat with the zinc halide here, like in the organo iron we have learned, and you are going to get in the palladium 0 as organo palladium reagent, you are going to get this compound, coupling compound. Okay, so where R and R is coupled here, and this is been removed. Okay, so this is how Negishi coupling means. Main thing is here, so zinc halide is very much important here. Okay, similarly the next Kumuda coupling. Okay, in Kumuda coupling also you can see same thing, alkyl halide is used, and here as usual, so Kumuda coupling always Grignard's MgX, R dash MgX is used. Again here palladium 0 as a catalyst is used here, and you are going to get the coupled product, that is your RR dash. Okay, so this is also the Kumuda coupling you can show, which is going to show very good result in the presence of palladium in the presence of palladium catalyst. Similarly, one more you can show is your Sonogo-Shira coupling. Okay, Sonogo-Shira coupling. So where you take again the alkyl halide and treat with the alkyne reagent R2. Sonogo-Shira always reacts with the alkynes here. Again here you can see the palladium catalyst is used along with the copper as a co-catalyst. Okay, and the base is very much important here. So base, and you are going to get R dash, this one. Okay, so coupling product we are going to get, that is this. So where R dash is going to R1 R2, I will take it as R1 and R2 here, because you have taken R1 and R2 here. So this is happening here in the presence of palladium as a catalyst and copper co-catalyst, and the presence of base. This Sonogo-Shira coupling happens and you are going to get the coupled product here. So this is what. And finally, one more reaction we can show for this palladium organo reagent, that is Hartwig coupling. Okay, Hartwig coupling. So this is one where you take again alkyl halide and you treat with this R dash. So this is secondary amine. Okay, secondary amine, you treat this with here 1 2 3 H. So here again in the presence of palladium in a 0 state and base, in the presence of base, you are going to get tertiary amine. You are going to get the tertiary amine as a product here. Now here palladium 0 is somewhat this is what it is taken as a catalyst, where you can see this palladium is been connected here with phosphine some other group this way. Okay, so this is how the catalyst is used, organo palladium catalyst, like what we have shown here, just palladium 0. So don't think that palladium in all the cases we have taken a reagent, so reagent will be in this way. So where palladium organo reagent catalyst is working in this way in most of the reactions, and you can see the and it is going to give the different results like this. Okay, so this is how in today's video we have completed the organopalladium organic reagent in synthesis of the organic compounds here. Okay, so hope you understood this. Now last one remained is your organo copper. Okay, last one is organo copper, so that will complete your unit 2 100%. Unit 2 will be completed 100%. Okay, so yesterday's video we have seen organo iron is over, this is also over. Okay, palladium is over now, organo this is left, so we will see in the next video. Thank you.